In the silent expanse of the night, we have always looked upward, seeking meaning in the tapestry of light scattered across the velvet dark. For millennia, humanity treated the stars as static markers, divine script etched upon the celestial sphere, unchanging and eternal. But beneath that perceived stillness lies a violent, dynamic reality, a clockwork of cosmic forces that govern not just the rotation of planets, but the very genesis and ultimate conclusion of existence itself. We find ourselves living within a fragile bubble of relative calm, suspended in a vast, roiling ocean of energy where matter is forged in the crushing pressure of stellar hearts and scattered across the void in cataclysmic explosions. This is the story of our universe, not as a static painting, but as an active, evolving, and terrifyingly vast engine. We are here to dismantle the myth of the immutable night sky and replace it with the breathtaking, often humbling, evidence of a universe that is fundamentally, inescapably, and perpetually in motion. When we observe the cosmos, we are actually looking backward through the deep corridors of time. The light reaching our eyes from the most distant reaches of the observable universe began its journey billions of years ago, traveling across the expanding fabric of space to finally strike the detectors of our modern observatories. It is a fundamental, established fact of astrophysics that we live in an expanding universe, a discovery that fundamentally altered our understanding of reality in the early 20th century. Before this realization, the prevailing consensus, even among the most brilliant minds of the era, was that the universe was steady, an eternal, unchanging stage. But the evidence, anchored in the work of astronomers like Edwin Hubble, shattered that comfort. By observing the redshift of distant galaxies, we confirmed that space itself is stretching, carrying the fundamental structures of our reality away from one another at accelerating speeds. This is not a matter of debate, it is a measurable, verifiable, and foundational cornerstone of modern cosmology. Yet, this discovery raises more questions than it answers, leading us into the realm of the genuinely disputed and the deeply mysterious. While we can map the expansion, we are currently grappling with the tension in our measurements, a discrepancy between different methods of calculating the Hubble constant that has left the scientific community in a state of high alert intellectual debate. Is our current model of gravity, our standard understanding of how the universe behaves at its largest scales, incomplete? Some experts point toward the potential for new physics, hidden variables that we have yet to grasp, while others suggest that our current observational techniques may contain subtle, systematic biases. This is science in its most honest, rigorous form, a process of staring into the unknown, admitting what we do not know, and refusing to settle for convenient, yet potentially incorrect, narratives. We are not just cataloging stars, we are interrogating the very nature of space-time. There are, of course, those who seek to fill these gaps in our knowledge with speculation, or worse, with claims that fly in the face of established physical laws. Occasionally, in the fringes of the scientific discourse, we encounter theories that attempt to posit the universe as a simulation, or a construct designed by intelligent agency, often leaning on misunderstood interpretations of quantum mechanics to grant their arguments a thin veneer of scientific legitimacy. It is vital to state clearly that these are speculative claims, often based on philosophical conjectures rather than empirical evidence. The scientific method demands that we explain the observable world through falsifiable, reproducible data. When we move away from this standard, we lose our grip on reality. The universe as we observe it follows consistent, mathematical rules. It does not require an external architect to account for its complexity. The beauty of the cosmos lies precisely in its ability to generate profound complexity from simple, elegant physical laws. To understand where we are, we must understand the ingredients of our existence. Everything we see, the trees, the mountains, the distant nebula, and the device you are using to view this documentary, is composed of atoms that were forged in the centers of stars. This is not poetic metaphor, it is verified, physical reality. When a star reaches the end of its life, it does not simply vanish. Depending on its mass, it might swell into a red giant, shedding its outer layers into a beautiful, glowing shell, or it might collapse under its own gravity, triggering a supernova, one of the most energetic events in existence. In that blinding moment of destruction, the elements necessary for life are synthesized and blasted out into the galaxy. We are, quite literally, the remnants of ancient star stuff, redistributed and repurposed over billions of years. This cycle of birth and death is the pulse of the galaxy, a process that continues today in the dense, swirling clouds of gas and dust known as stellar nurseries. These stellar nurseries are among the most chaotic and active regions of our galaxy. Within these colossal clouds, gravity begins to pull gas and dust together, creating dense, glowing regions where new stars ignite. We can see this occurring right now in the Orion Nebula, a sprawling expanse of ionized gas that acts as a crucible for stellar creation. When we study these regions using infrared telescopes, we can peer through the thick, obscuring dust that hides these nascent suns from the naked eye. We observe the accretion disks, swirling flat structures of gas and planetesimals that surround these young stars. This is the process of planetary formation in real time, a messy, violent, and fascinating collision of debris that eventually settles into the stable orbits we observe in our own solar system. It is a violent birth, often characterized by high-energy jets of matter being ejected from the poles of the young stars, clearing away the surrounding cocoons of gas to reveal the solar systems developing within. The formation of a planetary system is far from a delicate process. It is a chaotic, unpredictable, and remarkably efficient mechanism. For a long time, we wondered how common this process truly was. Were we a freak occurrence, an anomaly in a mostly empty and barren galaxy? The discovery of exoplanets over the past 3 decades has definitively answered that question. We now know, through extensive observations by missions like the Kepler Space Telescope and the Transiting Exoplanet Survey Satellite, that planets are the rule rather than the exception. Almost every star we observe has at least one planet orbiting it, and many possess multi-planet systems that bear striking, yet alien, resemblances to our own. This has transformed our view of the galaxy from a collection of isolated suns into a thriving, crowded neighborhood, filled with worlds that vary from icy, gas-shrouded giants to rocky, terrestrial planets orbiting in the habitable zones of their host stars. However, the sheer abundance of potential worlds does not equate to the abundance of life, a distinction that remains one of the most profound and unresolved questions in all of science. We have found the water, the organic molecules, and the energy sources necessary for life as we know it scattered across the cosmos, yet the phenomenon of life itself has proven to be elusive. This is the heart of the Fermi paradox. If the universe is so vast and so filled with life-supporting potential, then where is everyone? We look for signals, we scan the electromagnetic spectrum, and we analyze the atmospheres of distant exoplanets for biosignatures, yet we are met with an unsettling, profound silence. Some have speculated that we are alone, a solitary miracle in a vast, indifferent dark. Others propose that civilizations may arise and vanish in the blink of a cosmic eye, or that the distances involved are so immense that contact is fundamentally impossible. Both positions are speculative. The truth remains hidden behind the immense veil of space and time. As we continue to build our knowledge, we must be careful not to conflate technological advancement with omniscience. Our telescopes, while powerful, have limitations. Our theories, while robust, are subject to refinement and, occasionally, complete revision. This is not a weakness of science, it is its greatest strength. We have navigated our way from a geocentric model where we believed we were the center of all things, to a realization of our true, minuscule place in a vast, dark, and indifferent expanse. We have seen the evolution of stars and the formation of galaxies, and we have begun to map the history of our own origins to the very dawn of the universe. Yet, each discovery, each step forward, seems to open a door to 10 more rooms we have yet to explore. We have moved from the known to the unknown, and in doing so, we have discovered that the universe is far more bizarre and wonderful than we could have ever imagined. Consider the role of dark matter, an invisible substance that makes up the majority of the mass in the galaxy. We cannot see it directly, it does not emit, absorb, or reflect light. We only know it is there because of the way its gravity dictates the motion of the stars and galaxies around it. Without dark matter, the galaxies we see would simply fly apart. They lack the visible mass required to hold their own structures together. This is a profound, established scientific fact, yet the nature of dark matter remains a complete mystery. Is it a new type of subatomic particle? Is it a fundamental flaw in our understanding of gravity? Thousands of researchers are dedicating their entire careers to identifying this hidden ghost in the machine, running deep underground experiments to catch a single interaction, yet it remains elusive. It is a reminder that the world we interact with every day is merely the surface of a much deeper, more complex reality that remains largely hidden from our direct perception. The challenge of understanding dark matter is eclipsed only by the challenge of dark energy, the mysterious force that is driving the acceleration of the universe's expansion. Unlike dark matter, which pulls things together, dark energy pushes, acting as a repulsive force that is stretching space itself faster and faster every second. It is the dominant component of the cosmos, yet we understand almost nothing about it. It forces us to confront the reality that the vast majority of our universe is composed of something we can neither name nor see. It forces us to reconsider the ultimate fate of the universe. If dark energy continues to dominate, we are looking at a future where the galaxies drift so far apart that they will effectively become invisible to one another, leaving each island of stars alone in an ever-expanding, cooling, and empty void. This is not a theory born of despair, but a calculation born of observation, a logical endpoint to the expansion we measured decades ago. Despite these grand, intimidating forces, there is a tangible intimacy to the study of the stars. We are using our own ingenuity to reach out across the impossible distances. We are building machines that act as our eyes, our ears, and our hands in environments that would kill a human instantly. We are mapping the magnetic fields of stars, observing the collision of black holes, and tracing the migration of entire galaxies. Every instrument we point toward the heavens is a testament to the human desire to understand, to organize, and to find our place within the chaos. We are the universe observing itself, the manifestation of carbon and oxygen that has developed the ability to ponder its own origins. This realization brings with it a certain responsibility, a requirement to be stewards of the truth, to distinguish between what we have proven and what we have merely guessed, and to keep an open mind even when the findings are uncomfortable or counterintuitive. We are, in this very moment, standing at the precipice of a new era in astronomy. The next generation of observatories, both space-based and terrestrial, will provide us with a level of clarity that was previously impossible. We are preparing to peer deeper into the early universe, to look back toward the first light of the first stars, and to characterize the atmospheres of planets that are not just rocky, but potentially capable of hosting the precursors to life. We are entering a phase where the questions of the past, the ones that once seemed like philosophy or science fiction, are becoming the subject of hard, data-driven investigation. We are closing the gap between the observer and the observed, but the distance remains vast. As we prepare to delve into the mechanics of these celestial engines, we must prepare to leave behind the comforting simplicity of the night sky we once knew and embrace the cold, brilliant, and complex truth of the universe as it actually exists. The transition from the scale of the galaxy to the inner workings of a singular star requires a shift in perspective. We must move from looking at the broad brushstrokes of the cosmos to examining the fine, intricate details of stellar chemistry. It is within the core of a star that the fundamental rules of thermodynamics and quantum mechanics collide, creating the very energy that prevents the star from collapsing under its own massive weight. To understand the light that hits our eyes, we must first understand the fusion that occurs in the crushing heat of the stellar furnace. It is here that the narrative of our universe truly begins to tighten, moving from the movement of the masses to the dance of the atoms, setting the stage for a deeper exploration into how stars, the very crucibles of reality, live, breathe, and ultimately, die. At the heart of every star lies a high-stakes gamble between two colossal, opposing forces. On one side, the relentless, suffocating pull of gravity, a force that seeks to crush everything inward toward a single point of infinite density. On the other, the outward pressure generated by nuclear fusion, a process that converts the very fabric of matter into pure, radiant energy. This state of equilibrium is known as hydrostatic balance, a delicate standoff that can last for billions of years. When a star is stable, like our own sun, it is essentially a self-regulating machine, balancing its internal pressure against the overwhelming weight of its own mass. But this is not an infinite state of grace. Every second, the star is consuming its own fuel, turning hydrogen into helium through the proton-proton chain, a series of interactions governed by the strict, unforgiving laws of quantum mechanics. The star is, quite literally, burning its own foundations to keep the lights on, and eventually, the fuel will run out. The interior of a star is an environment that defies human experience. We describe it in terms of millions of degrees and pressures that would collapse an atom into a fraction of its size, yet these numbers fail to capture the visceral reality. In the core, protons are forced together at such immense speeds that they overcome the electromagnetic repulsion that usually keeps them apart. This allows the strong nuclear force to take hold, binding them into helium nuclei. The mass of the resulting helium atom is slightly less than the sum of the original protons, and that lost fraction of mass is transformed into energy, following Einstein's famous equivalence, E equals mc squared. This minuscule loss of mass, multiplied by the speed of light squared, produces the staggering amount of energy that sustains the star. It is a process of relentless, high-energy transformation that fuels the brilliance of the entire cosmos. However, the transition from hydrogen burning to the next phase of a star's life is where the narrative of stellar evolution takes a turn toward the dramatic. As hydrogen supplies dwindle in the core, the outward pressure weakens. Gravity, ever present and waiting, immediately gains the upper hand, causing the core to contract. This compression generates even more heat, which begins to ignite the outer layers of the star, causing them to expand and cool. The star transforms into a red giant, a bloated, luminous specter that can grow hundreds of times larger than its original size. In this phase, the star is a dying giant, desperately trying to find a new source of fuel to stave off the final collapse. It begins to fuse helium into heavier elements like carbon and oxygen. This is a crucial threshold in the history of the universe, because it marks the point where the universe shifts from a simple chemistry of light elements to the complex, heavy element factory that makes life possible. The internal structure of these dying stars becomes onion-like, with layers of different elements fusing at different depths. Each new layer of fusion buys the star a little more time, but the returns are diminishing. The fusion of iron, however, is where the process hits a brick wall. Fusing iron consumes energy rather than releasing it, which means that as soon as a star begins to produce iron in its core, it has effectively signed its own death warrant. There is no more outward pressure to hold back the weight of the star. In a fraction of a second, the core collapses, creating a shockwave that rips the star apart in a supernova, or in the case of less massive stars, causing them to shed their layers in a slow, graceful death that leaves behind a dense, white dwarf. The complexity of these final moments is staggering, yet the mechanisms are strictly dictated by the internal laws of physics. Beyond the life and death of individual stars, we must consider the architecture of the galaxies they inhabit. When we look at a spiral galaxy, we are observing a grand, rotating graveyard and nursery combined. The motion of stars within a galaxy follows a pattern that, for many years, puzzled astronomers. According to the laws of orbital mechanics, stars further out from the galactic center should move slower than those closer in. Yet, when we measure the rotational speeds of stars in the outer reaches of spiral galaxies, we find that they are moving just as fast as those near the core. This is a well-established observation that points toward the existence of something we cannot see. The visible matter, the stars, the gas, the dust, is simply not enough to provide the gravitational pull necessary to keep these outer stars in their orbits. This is the primary observational evidence for dark matter, a substance that exists in a halo around the galaxy, acting as an invisible anchor that prevents the structure from flying apart. Some theorists have suggested that this discrepancy might be explained by modifying our understanding of gravity itself, proposing frameworks like MOND, or modified Newtonian dynamics. These models attempt to account for the rotational speeds of galaxies without invoking unseen particles, by suggesting that gravity behaves differently at extremely low accelerations. It is important to distinguish this as a field of genuine scientific dispute. While MOND can successfully predict the rotation curves of many galaxies, it struggles to explain the larger, cosmological observations that dark matter explains so elegantly, such as the patterns seen in the cosmic microwave background radiation or the way light bends around massive clusters of galaxies. The scientific consensus currently leans heavily toward the existence of dark matter as a form of non-baryonic particle, but until we can directly detect this particle, the door remains open for alternative interpretations. It is a testament to the rigor of science that we continue to test these competing models against the cold, hard data provided by our most sensitive instruments. The interplay between dark matter and visible matter shapes the large-scale structure of the universe, creating a cosmic web of filaments and voids. Gravity acts as the architect, drawing matter toward the densest regions of the dark matter halos, where galaxies cluster together in vast, sprawling metropolises. These clusters are the largest bound structures in the universe, containing hundreds or thousands of galaxies, each locked in a slow, gravitational dance. Within these clusters, galaxies interact, colliding and merging in a process that reshapes their very nature. An elliptical galaxy, for instance, is often the result of two spiral galaxies colliding, their stars scattered and their organized rotation disrupted into a chaotic, swarming system. These collisions are not just events of destruction, they are sites of intense star formation, where the sudden compression of gas clouds triggers a firestorm of new stellar births. As we peer deeper into these clusters, we are reminded of the scale of our ignorance. We are currently in the midst of a data revolution, where surveys like the Vera C. Rubin Observatory will soon provide us with a high-definition map of the night sky, capturing millions of galaxies and their movements over time. This will allow us to test the influence of dark energy with unprecedented precision. If dark energy is indeed a cosmological constant, an inherent energy of space itself, then its influence should be consistent across time. If it changes, or if it has a dynamic nature, then our entire model of the universe's history will need to be rewritten. This is not a cause for concern, but for excitement. The ambiguity of our current understanding is precisely what drives the next generation of researchers to build better, more sensitive, and more innovative detectors. We are moving from a phase of observation to a phase of high-resolution simulation and testing. The history of our understanding of these cosmic forces is a narrative of shedding our own biases. For a long time, we viewed the universe as a reflection of our own human need for permanence. We named constellations after heroes and gods, projecting our own myths onto the stars. We assumed the vacuum of space was empty, a void between points of light. Today, we know the vacuum is a churning field of energy, and the stars are not eternal, but finite, burning candles in a vast, dark room. We have replaced the myth of the static, divine sky with the reality of a universe that is a living, breathing, and expanding entity. This transition is not a loss of wonder, it is an expansion of it. The reality of a supernova, a process that creates the iron in our blood and the calcium in our bones, is far more poetic and meaningful than the myths we once used to explain the world. We find ourselves in a unique position in the history of science. We have enough data to know that the universe is governed by laws we can understand, yet we have enough mystery to ensure that the process of discovery is far from over. We are at a moment where the tools of physics, astronomy, and computer science have converged to allow us to model the entire lifespan of a galaxy in a virtual environment. We can watch a galaxy evolve from the early, turbulent era of the universe to the mature, stable structure we see today. By comparing these simulations to the light we capture from billions of light years away, we can refine our understanding of the initial conditions of the cosmos. This process is the ultimate interrogation of the universe. We are asking the cosmos to reveal its secrets, and by listening closely to the faint, ancient echoes of its history, we are beginning to translate the answers into our own language. As we look toward the next stages of this journey, we must be prepared to confront the limits of our own perception. Our human minds are evolved to understand the movement of objects on a scale of meters and seconds, not parsecs and billions of years. We grapple with dark matter because it doesn't fit our everyday intuition. We struggle with the concept of the expansion of space because there is no center and no edge in our conventional way of thinking. Yet, the math holds firm. The gravity that binds a galaxy is the same gravity that pulls an apple to the ground. The light from a quasar billions of light years away is governed by the same atomic transitions as the light from a street lamp. This continuity is the bridge that allows us to travel from our small, terrestrial home into the heart of the most energetic regions of the cosmos. It is this continuity that provides the foundation for everything we know, and everything we have yet to discover. The story of the universe is not just about the massive, the distant, and the invisible. It is also the story of how those forces have conspired to create a planet that is stable enough, and long-lived enough, to allow for the development of consciousness. We are the beneficiaries of a series of cosmic coincidences that started with the Big Bang and continued through the cooling of the universe, the formation of the first stars, and the enrichment of the interstellar medium with heavy elements. Every step of this process was necessary for us to exist. When we consider the sheer probability of this outcome, it can feel overwhelming, perhaps even random. But the deeper we dig into the mechanisms of stellar and galactic evolution, the more we see that the laws of physics are not just random chance, they are the blueprints for a universe that, by its very nature, tends toward the formation of structures and the emergence of complexity. We are, therefore, a part of the system we are studying. We are not just spectators, but participants in a chain of events that links the first atoms to the last thoughts of a dying star. This perspective changes our relationship with the cosmos. It shifts the focus from a search for external meaning to a realization of internal connection. The light from the stars we see tonight is a message that has traveled through space and time to find us. It carries the history of our origin, written in the spectral lines of hydrogen, helium, and the heavier elements that our own bodies are built from. To study the universe is to study ourselves, and to push the boundaries of what we know is to push the boundaries of what it means to be alive in such a vast, magnificent, and ultimately knowable expanse. But to truly understand how these forces of creation and destruction culminate in the existence of complex planetary systems, we must narrow our focus once more. We must transition from the life cycles of stars to the chaotic, transformative period of planetary formation itself. As a star ignites and clears its surrounding disk, the remaining material is left to settle into a new, stable configuration. How do these remnants of the stellar birth process transition from chaotic, colliding dust into orderly, orbiting worlds? The answer lies in the volatile, high-velocity world of protoplanetary disks, where the fundamental rules of gravity, collision, and accretion begin to build the very planets that we, today, are beginning to count across the distant reaches of our galaxy. The process of planetary assembly begins in the swirling, turbulent debris of the protoplanetary disk. Here, the sheer density of dust and gas creates a microscopic, high-speed collision course. We are talking about particles no larger than grains of sand, colliding at velocities that initially cause them to stick together through electrostatic forces, the same forces that allow static electricity to cling to a screen. Over thousands of years, these tiny aggregates collide and fuse, growing from microscopic dust bunnies into pebbles, then boulders, and eventually, into planetesimals. These are the building blocks of planets, rocky bodies that range in size from a few kilometers to the scale of our moon. This phase of development is characterized by a violent, chaotic hierarchy where the strongest gravity wins. The larger a body becomes, the more effective its gravitational reach, allowing it to sweep its orbital path clear of other debris, effectively cannibalizing its neighbors to feed its own growth. It is a misconception to view this as a clean, orderly process. The early solar system is better described as a demolition derby. Once planetesimals reach a sufficient size, they exert gravitational influence on each other, leading to high-velocity impacts that can either shatter a world entirely or contribute to its mass. This is the era of the Great Collisions, a time when our own solar system witnessed the birth of the Moon from a glancing impact between the proto-Earth and a Mars-sized body known as Theia. This event, supported by the geochemical analysis of lunar samples brought back by the Apollo missions, is an established fact of planetary evolution. The isotopes of oxygen found in lunar rocks are nearly identical to those on Earth, suggesting a common origin born from the same violent mixing of debris. This was not a unique occurrence, it is a signature feature of planetary formation throughout the cosmos. Beyond the inner, rocky regions of a young system, the dynamics shift significantly. As we move past the frost line, the distance from the star where temperatures drop low enough for volatile compounds like water, methane, and ammonia to condense into ices, the raw materials for planet building become exponentially more abundant. In these cold reaches, the rapid accumulation of gas and ice allows for the creation of giants. These worlds, massive enough to capture vast envelopes of hydrogen and helium from the collapsing nebula, grow into the gas giants and ice giants we see in our own system. Their formation is a gravitational race. If a core can grow large enough, quickly enough, it can initiate a runaway accretion process, vacuuming up the surrounding gas before the young star's stellar winds can blow it away. This explains why we see such diversity in the masses of exoplanets. Some systems lack the timing or the raw material to form these giants, while others form several, leading to highly dynamic systems where planets can be tossed into extreme, elliptical orbits by their own gravitational interactions. The architecture of these systems is not necessarily permanent. In the early, crowded stages of a planetary system, gravity is a volatile architect. We have observed, through both computer modeling and direct observation of exoplanetary systems, that planets can migrate. They do not always stay where they were born. Friction between a planet and the disk of gas and dust can cause it to spiral inward toward its host star. This phenomenon explains the existence of hot Jupiter's gas giants that orbit so close to their suns that they complete an orbit in mere days, possessing temperatures that would vaporize lead. These planets could not have formed in such a scorching environment. They were born in the cold depths of the outer system and migrated inward, a process that would have undoubtedly cleared out or destroyed any smaller, rocky worlds that occupied those inner regions during their journey. This realization has forced us to abandon the idea that our own solar system's arrangement, with small, rocky planets inside and giants outside, is the only way a system can look. We now understand that planetary architecture is a product of history, a series of gravitational encounters, migrations, and cataclysms that define the final state of the system. This brings us to the fascinating, genuinely disputed field of planetary migration theories. While we have strong evidence that migration occurs, the exact mechanisms, whether it is driven by gas disk interactions, planet-to-planet scattering, or the influence of an unseen companion star, remain topics of intense research. We are currently testing these hypotheses by looking for patterns in the orbital resonances of distant systems. When we find two planets with orbital periods that are locked in a simple, integer ratio, it provides a window into their past, suggesting they arrived at their current positions through the subtle, gentle migration dictated by the gas disk rather than the violent, chaotic scattering caused by planet-planet interactions. As these systems stabilize, they enter a long, cooling phase. The intense heat of formation slowly radiates away into the vacuum, and the geological activity of the planets begins to set the stage for long-term evolution. This is where we must distinguish between the mere existence of a planet and its habitability. A planet might be positioned in the habitable zone, where temperatures allow for liquid water, but that is only the first requirement. To sustain an environment that can support the complex chemistry of life, a planet needs more than just location. It needs a magnetic field to shield it from stellar radiation, a stable atmosphere to regulate its temperature, and the right mix of chemical precursors. We have learned that these factors are not guaranteed. Mars, for instance, once likely possessed a thicker atmosphere and liquid water on its surface, as evidenced by the dry riverbeds and mineral signatures mapped by our rovers. The loss of its magnetic field, likely due to the cooling of its core, allowed the solar wind to strip away its atmosphere, turning a potentially wet world into a frigid, barren desert. This highlights a critical lesson in our quest to understand the universe. Stability is fragile. The geological activity of a planet, driven by its internal heat and the decay of radioactive isotopes in its mantle, is the ultimate engine of long-term climate control. Plate tectonics, which cycle carbon and other essential elements between the crust and the atmosphere, serve as a planetary thermostat. Without this, a planet might descend into a runaway greenhouse effect, as we see on Venus, where the atmosphere became so thick and oppressive that it could melt lead on the surface. Understanding why Earth maintained its temperate balance while our neighbors swung into extremes is a top priority of planetary science. It requires us to look not just at the planet's size and distance, but at its internal composition and its history of volcanic outgassing, which pump the necessary greenhouse gases into the air to jumpstart the cycle of life. We are currently on the verge of being able to probe these atmospheres on a routine basis. Using the technique of transit spectroscopy, we can observe the light from a distant star as it passes through the atmosphere of an orbiting planet. The molecules in the atmosphere absorb specific wavelengths of that light, leaving a chemical fingerprint that we can detect with our spectrometers. This is not science fiction, it is a current, active, and rapidly advancing field of study. We are beginning to detect water vapor, carbon dioxide, and methane in the atmospheres of distant, gas-rich worlds. While these are not yet definitive biosignatures, they are the necessary precursors. We are essentially learning how to read the breath of alien worlds, deciphering the composition of skies that no human eye will ever witness, and in doing so, we are narrowing the search for the conditions that make life possible. Yet, we must remain grounded. Even with the discovery of thousands of worlds, the leap from a habitable environment to a living one remains a mystery. We see the potential everywhere, but we have yet to see the evidence of biology beyond our own. Some speculate that the transition to life is a rare, improbable event, a great filter that prevents most planets from ever developing complex organisms. Others argue that if the building blocks are common and the conditions are right, life should be a natural, even inevitable outcome of chemical evolution. This remains one of the most significant open questions in science. We have mapped the path from star to planet, and from planet to chemistry, but the spark that turns the chemical into the biological remains an enigma. We are looking for the point where inanimate matter crosses the threshold into the active, self-replicating realm of life. The complexity of this challenge is why we have expanded our search beyond simple, Earth-like analogs. We are now considering ocean worlds, moons like Europa and Enceladus, which harbor vast, liquid water oceans beneath thick, icy crusts. These environments are shielded from the radiation and fluctuations of the surface, powered by the tidal forces exerted by their parent gas giants. The heat generated by this constant squeezing and stretching is sufficient to maintain liquid water, even in the cold outer solar system. These hidden, submarine environments could be the most common habitats for life in the entire galaxy, existing in complete isolation from the stars they orbit. This perspective shifts our thinking from planets that look like Earth to worlds that look like nothing we have ever considered, expanding our definition of where and how life might emerge. As we look toward the future, we must recognize that our exploration of the universe is still in its infancy. We have spent only a few generations looking through telescopes, yet we have already rewritten the history of the cosmos. We have discovered that we are not at the center, that the stars are not eternal, and that the elements of our own bodies were forged in the final, cataclysmic gasps of dying suns. We have found that the galaxy is teeming with planets, and that we are, in a very real sense, the children of the stellar cycle. But we are also the explorers of this cycle. With every mission we launch, with every byte of data we analyze, and with every theory we test against the cold, hard data of the heavens, we are adding another chapter to a story that began nearly 14 billion years ago. The challenge now is to look at this vast, interconnected system not as a disconnected set of phenomena, but as a unified whole. From the dark matter that holds the galaxies together to the microscopic grains of dust that build planets, every part of the universe is linked by the same physical laws and the same history. We are beginning to see the patterns that weave these disparate elements into a coherent tapestry. As we move further into this era of discovery, the boundaries between disciplines are fading, replaced by a holistic understanding of how the cosmos functions as a single, evolving entity. We are no longer just looking at the stars, we are looking at the machine that makes them, the chemistry that fuels them, and the worlds that emerge in their shadows. Our next steps into this uncharted territory will bring us closer to the most profound questions of all. We are moving from simply observing the universe to understanding the rules of its operation, from wondering where we come from to mapping the process of our own creation. As we refine our tools and expand our reach, we are preparing to uncover the deep, underlying mechanisms that govern the transition from the simple, primordial soup of the early universe to the complex, biological realities we inhabit today. We have traced the origin of the atoms, the birth of the stars, and the assembly of the planets. Now, as we stand on the threshold of a deeper understanding, we must prepare ourselves to investigate the final, most elusive piece of this cosmic puzzle, the emergence of consciousness itself within this vast, physical engine. The journey from the inert to the sentient represents the final, most daunting frontier in our exploration of the cosmos. Having mapped the trajectory from the furnace of a star to the complex geological activity of a planetary surface, we arrive at the most intimate mystery of all, the transition from chemistry to biology, and ultimately, to the observer. This is not merely a matter of biological classification. It is a question of whether the fundamental laws of physics are implicitly tuned toward the emergence of complexity. Some scholars suggest that the universe operates according to a principle of self-organization, where the complex systems we call life are an inevitable thermodynamic consequence of entropy being forced through the cooling, structured environments of stable planets. This is not to say life is guaranteed on every rocky world, but rather that the physical scaffolding of the universe is not hostile to the formation of informational complexity. When we examine the rise of life on Earth, we see a path carved through billions of years of trial and error, a process of molecular scaffolding that eventually yielded the self-replicating capacity of RNA and DNA. To understand how this occurred, we must look to the extremophiles on our own planet, the microscopic organisms thriving in conditions we once deemed lethal. We find life living in the acidic, boiling vents of the deep ocean floor, far from the reach of the sun, deriving energy from the chemical reactions between water and rock. We find organisms thriving in the sub-zero, radiation-drenched ice of Antarctica and in the parched, hypersaline soils of the Atacama Desert. These survivors demonstrate that life is not a fragile, precious anomaly that only exists in temperate gardens. It is a tenacious, adaptable force that can seize any energy gradient it finds. This shift in our understanding, from looking for Earth-like twins to looking for habitable environments, is the most profound change in astrobiology. We are essentially expanding our definition of life to include any system capable of maintaining a low entropy state by processing energy from its environment, a definition that applies just as well to a deep-sea hydrothermal vent as it does to a potential lake of methane on Titan. However, we must navigate this landscape with extreme intellectual caution. While we have proven that the chemical ingredients for life are ubiquitous across the galaxy, the gap between prebiotic chemistry and biological entity remains an unsolved scientific mystery. We often hear claims that life must be common because the universe is vast, or that life is a rare fluke because we have yet to detect a single radio signal. Both of these are speculative assertions, not established facts. We currently possess a sample size of exactly one, our own biosphere. We are analyzing this single data point to build models for the entire universe, a process that is as necessary as it is prone to error. When we talk about the Drake equation or the probabilities of alien civilizations, we are effectively plugging in variables based on our own limited experience. We do not yet know if the origin of life is a common result of chemical evolution or a singular event of such low probability that it may have occurred only once in the entire observable expanse. This uncertainty does not diminish the value of our search, it elevates it. The fact that we are currently designing missions to probe the subsurface oceans of moons in our own solar system is a testament to our commitment to data-driven inquiry. We are not assuming life is there, we are going to look for the markers of metabolism. By analyzing the ratios of isotopes in these distant environments, we may eventually identify signatures of biological processes that differ from the random, chemical fluctuations of an abiotic world. This is the rigorous, slow, and often frustrating work of science. It involves constructing instruments that can withstand the crushing pressures of an icy crust and the radiation of a gas giant, all to answer a question that has haunted humanity since we first looked at the moon and wondered if we were the only ones looking back. As we peer into these depths, we must also reflect on what it means to be the observer in this vast system. We are the result of a 14 billion year process of physical refinement. The iron in our hemoglobin was birthed in the core of a dying star, the calcium in our skeletons was recycled through the crust of an evolving planet, and the electricity flickering through our neurons is a reflection of the same fundamental forces that drive the expansion of the universe itself. We are, quite literally, the cosmos becoming aware of its own existence. This is not a poetic sentiment, it is a description of the material continuity that links the subatomic, the stellar, and the cognitive. We are the eyes and the mind of the universe, the entity through which the cosmos probes its own structure, its own origins, and its own ultimate fate. This realization brings with it a certain weight of perspective. For a long time, we viewed our scientific progress as a way to conquer or master the natural world. We thought of the universe as a resource to be measured and claimed. But as we have learned more, that perspective has shifted toward one of humble integration. We are a part of a larger, coherent system that operates on scales far beyond our individual comprehension. When we analyze the light from a distant quasar, we are essentially looking at the ancient history of our own local environment. When we compute the gravitational dynamics of a black hole, we are testing the limits of the same laws that keep our own feet on the ground. We are learning that there is no us versus the universe. There is only the universe, interacting with itself through the lens of human discovery. The complexity of our position becomes even more striking when we consider the passage of time. We live in a brief, vibrant epoch of the universe's history. The stars are burning at a rate that allows for the creation of life-supporting planets, but this will not last forever. In the distant future, the galaxies will be so far apart that the light from one will never reach the other. New stars will cease to form as the reservoirs of cold gas are exhausted, and the universe will settle into a long, cold, and dark period of decay. To be alive at this specific moment, when the stars are bright and the information is still reaching us from the far corners of the cosmos, is a privilege of cosmic timing. We are here during the most active phase of the universe's life cycle, a window that allows us to witness the unfolding of the drama we have spent these last few minutes, and indeed these last few centuries, attempting to understand. It is easy to look at the vast, uncaring scale of the cosmos and feel a sense of insignificance. We are, after all, inhabitants of a small planet circling a mundane star on the edge of a typical spiral galaxy. But this perspective misses the fundamental point of our discovery. The size of the universe is not a measure of our unimportance, it is the canvas upon which our capacity for understanding is displayed. The fact that we have used our limited time and resources to map the history of space and time is our defining characteristic. We have taken the raw, chaotic energy of the Big Bang and organized it into the concepts of physics, chemistry, and biology. We have turned the silence of the void into a language of mathematics and observation. As we look toward the future, we must commit ourselves to this rigorous pursuit of truth, regardless of where it leads. If our models turn out to be wrong, we will revise them. If our theories are found to be incomplete, we will expand them. The beauty of the scientific method is not that it provides us with immediate, comfortable answers, but that it forces us to confront the truth of our reality, however counterintuitive it may be. We are moving from the era of speculation to the era of precision. We are building the tools that will allow us to map the unseen, to characterize the distant, and to perhaps one day touch the very surfaces of worlds that we have only ever seen as points of light in a telescope. The story we have explored here is not finished. It is perpetually ongoing. It is a narrative of matter evolving into complexity, of energy flowing through structured systems, and of a species rising to the challenge of understanding its own place within the machinery of the cosmos. We have moved from the myth of the static heavens to the reality of the dynamic universe, and in that transition, we have found something much more profound than the stories we once told ourselves. We have found a reality that is vast, complex, and deeply interconnected, a reality that requires us to be both the observers and the participants in an unending process of inquiry. Everything we see, everything we touch, and everything we think is a testament to this process. From the smallest atom in our bodies to the largest structure in the universe, we are all part of the same grand, unfolding, and deeply beautiful story. We are the product of the stars, the witnesses to the evolution of the galaxy, and the architects of our own understanding. As we turn our eyes back to the night sky, we no longer see a collection of static, divine lights. We see the past, the present, and the potential for a future that we are building with every observation we make. The universe is not a closed book of fixed truths, it is a living, breathing, and ever-expanding mystery, waiting for us to continue the work of unraveling its threads. In the end, our search for the cosmos is our search for ourselves, and that search, in its persistence and its wonder, is the most noble undertaking in the history of human existence. The stars continue to burn, the galaxies continue to drift, and we, the descendants of the ancient stellar nurseries, will continue to look upward, seeking to understand the brilliant, cold, and beautiful reality that we call home.